Hello and welcome to Zeta Explained. Today we are going to talk about the mean value theorems of zeta. And by mean value theorems, what I mean is that we're going to take a vertical line in the complex plane and analyze what the zeta function looks like along such a line. And in particular, we're going to analyze the average value of zeta across such a line. And this is different from what we've done in some of the previous episodes. In the previous episodes in 25 and 36 in particular, we looked at the big O and big omega growth rates, which sort of mean the upper bound and lower bounds across such lines. And we figured out results when sigma is which is the real part, so where the line is, where sigma is greater than 1 or equal to 1. But it's actually very hard to kind of analyze this when the real part is less than 1. So when sigma is less than 1, then it's a very hard question. In fact, it's an open question of what the best big O bound is for the zeta function inside the critical strip, so the region between 0 and 1. And as an example, the Lindelof hypothesis is that zeta of 1/2 plus it is equal to O of t to the epsilon for all epsilon greater than 0, but the current best bound is only t to the 13 over 84 plus epsilon. So there's still a bunch of open questions about what the growth rate of zeta is inside the critical strip. So instead of trying to tackle these very hard questions, I'm going to go over an easier question, that has been answered, or at least of this simple form has been answered, but there are still more general forms that we're not going to talk about today. The simpler class of questions concerns the average value of zeta along such a line as opposed to the highest or lowest value. So in particular, we're concerned with the integral of this form, so 1 over t times the integral from 0 to t of zeta of sigma plus it and the absolute value squared of that dt as t goes to infinity for a given value of sigma. And these theorems are known as mean value theorems. So it's not to be confused with the mean value theorem in calculus. It has nothing to do with that. Okay, so let's kind of talk about the background. So the Riemann zeta function, zeta of s, is defined as the sum from n equals 1 to infinity of 1 over n to the s. This converges in the region where the real part is greater than 1, and we're going to write out s as sigma plus it. This is as usual. And in episode 31, we discussed Dirichlet series, which really mean that instead of the numerator being 1, the numerator can be kind of any function. And in particular, we found that zeta of s to the kth power is equal to the sum from n equals 1 to infinity of d sub k of n over n to the s, and where d sub k of n is the generalized divisor function. And this is the number of ways to multiply k divisors to get n, where the order matters. And today we're not really going to talk much about the number theory or the interpretation of d sub k of n, because we're mostly going to just use the fact that d sub 1 of n is just equal to 1, so it becomes the Riemann zeta function. But we will use the number theory result that for any k, d sub k of n is big O of n to the epsilon for all epsilon greater than 0. And in particular, what we're going to do is, for the first result we're going to prove, the first theorem, we're going to actually use the generalized d sub k of n, so zeta to the kth power. But then in the harder results, we're only going to focus on the first power of zeta, so not, or the first/second power of zeta, not the general power of zeta. Okay, so we're going to do the typical math thing at first, where instead of answering a simple question, we're going to consider the generalized question. So theorem 1, for a fixed sigma greater than 1 and a fixed positive integer k, then the integral from 0 to t of the absolute value of zeta of sigma plus it to the 2kth power dt is equal to this sum times t plus a couple of big O error terms. And in particular, if you were to set k equal 1 in this equation, then the left side is to the second power instead of to the 2kth power, just k equals 1. And then on the right side, then if d sub k of n, well, if k is 1, then d sub k of 1 is just 1. So then this becomes the sum of n equals 1 of 1 over n to the 2 sigma. And if you get 1 over n to the 2 sigma, sorry, drawing is not very good, 1 over n to the 2 sigma, then that's just the same as zeta of 2 sigma, because s is equal to 2 sigma here. So therefore, if you take a fixed sigma greater than 1, and you take the limit as t goes to infinity of 1 over t times this integral, so if we add a 1 over t to both sides, of this equation, then you'll get that this t kind of goes away, and then this 2 becomes a 1, and then this becomes a 1 over t. So let's get rid of this for now, because I've distributed it inside. And then if this thing is just 1, then this becomes zeta of 2 sigma. So remember, we said the sum of 1 over n to the 2 sigma is just zeta of 2 sigma. And then this term, because sigma is greater than 1, then this term will go to 0 because we can just find an epsilon small enough so that 1 minus sigma will be negative. T to a negative power goes to 0 as t goes to infinity. And then this is O of 1 over t, and that also goes to 0. So both of these terms go away. And that's how you get this corollary if you believe the theorem. And we're going to prove the theorem first, and then the corollary will follow from that. And in particular, what this corollary means is that if we take this green line, so for any fixed sigma greater than 1, so as long as this green line is to the right of 1, then the average value of the absolute value of zeta of sigma plus it squared on this line, so 1 over t times the integral from 0 to t of something is sort of the average along that line, is going to be zeta of 2 sigma. So in this diagram, the green line is on the line real part of s equals 1.5, so 1.5, and therefore this theorem in the corollary says the average value along this line really is just zeta of 2 sigma, in this case zeta of 3. So it's kind of interesting that you can relate the average value of a function along a line to another point of, along that function. Okay, and then we're going to go through the proof, and throughout the proof, I'm going to often compare a sum to an integral for the big O approximation. And this is kind of called the integral test from calculus, but I'm going to say for a real number a less than -1, then the sum from n equals t, I guess this should say n equals here, but maybe it's clear what I'm summing over, n equals t to plus 1 to infinity of n to the a power is equal to big O of the integral from t to infinity of x to the a dx. And to see this, you can just kind of imagine this thing that you might have seen before in elementary calculus. So if I take t equals 2, then it's the sum from 2 to infinity of, this, of whatever this is, and this is just strictly less than the integral from 1 to infinity of the same function. So therefore, this thing is big O of this integral. If you evaluate the integral, you get this. And if you kind of evaluate the limits of the integral, you get t to the a plus 1 power. Okay, so we're going to just use this a lot. Okay, so here's the start of the proof. So we're going to use the Dirichlet series expansion. So remember, zeta to the kth power of sigma plus it is the sum from n equals 1 to infinity of d sub k of n over n to the sigma plus it. And now I'm going to split out this sum into a finite sum and an infinite sum. The finite sum is where n is less than or equal to t, and then the infinite sum is just this part, the sum from n equals t plus 1 to infinity of the same thing. And then using this integral test that I mentioned, I'm just kind of listing out the explicit steps of the integral test here. Remember that d sub k of n, we said before, is O of n to the epsilon for any epsilon greater than 0. So that's where this epsilon comes from. And then in a big O, we don't care about this it part at all because a real number to an imaginary power is just, that doesn't affect the magnitude of the number at all. So in a big O, we only care about the size of a number or the, the modulus. So we don't care about the imaginary part. So therefore, this thing is just n to the minus sigma plus epsilon. And if you just do the integral test, this sum turns into an integral, and then you evaluate the integral and you get this term. So I'm saying that this infinite sum can be split up as a finite sum, and then this remainder big O for the infinite sum. And now we're going to call this term S and this term R. So you can think of it as a sum. So this thing is a sum, and this thing is a remainder, S plus R. And therefore, the integral that we're trying to evaluate is this. So the integral from 0 to t of the absolute value of zeta of sigma plus it then to the 2kth power dt is equal to the integral from 0 to t of the absolute value of s plus r squared dt. And this kind of just follows from our definition over here. Okay, and then using the triangle inequality, you'll note that here I'm just summing a positive number. Remember, the absolute value, even if s and r are complex values, the absolute value of this is a real number, and squaring is still a real number. So I guess one thing I should mention is that even though we're looking at complex functions and complex values everywhere, because anytime we're taking an integral, we're only integrating real numbers with the absolute value, then we're actually not doing any complex analysis this episode. This is all kind of real analysis or real calculus. Okay, so by the triangle inequality, the absolute value of s plus r is just less than or equal to the absolute value of s plus the absolute value of r. So that's why this is true. And then you can rewrite this thing as a binomial expansion. So s plus r squared. When I'm saying it out loud, I'm just sometimes dropping the absolute value sign. So s plus r squared is equal to s squared plus r squared plus 2sr. And remember, integrals are linear, so you can split these things out. And I'm going to call this last term 2u. So this integral is u. And then I'm going to say u squared, which is equal to this thing squared, just by definition, is less than or equal to this thing, where I'm kind of splitting out the squares by the integrals themselves. And this thing is called the Cauchy-Schwarz inequality, so this thing right here. And Cauchy-Schwarz is just a result about inner products. So you can think of the integral from 0 to t of some function as kind of a norm of a function. If this doesn't make sense, I would usually think of this as a linear algebra result. But you can also just think of this particular thing as just a thing about integrals, but I'm not going to prove this. This is a kind of more of a general math result. And now, remember, we're trying to figure out what this integral is, and we split it into 3 parts. And the first part I'm going to call the s term. The second part is the r term. And the third part is this u term with the Cauchy-Schwarz inequality. But because of this inequality, we can write this term in terms of the first 2 terms. Remember, it's just this and this. So we figure out the growth rate of s, the s term, and the growth rate of the r term, then we can figure out the growth rate of this whole thing. So I'm going to claim the easy part is the r, and then the s part is going to be much harder. So the r is we're going to cover right here, takes about a fifth of a page, and the s term is going to take like 2 pages later on. So the r, remember the integral from 0 to t of r squared dt. Remember, r is this big O, so if you square this, it goes from 1 minus sigma plus epsilon to 2 minus 2 sigma plus 2 epsilon. And remember, this is a function of big T. This is big T to some power, not little t to some power. So therefore, this is basically just a constant, so you can pull this out of the integral, and then the integral from 0 to big T of just 1 dt is just big T, so we're raising the exponent by 1. And then I'm going to use the fact that 1 minus sigma is less than 0, so this big O here, 3 minus 2 sigma, is O of 2 minus sigma. But we're going to use both results here later on. We're going to directly use this result as well, but we'll also kind of write this as well. Okay, so now we have to evaluate the s case. This is much, much harder. So we're trying to figure out the integral from 0 to t of s squared dt, where this is s. And we're going to use a fact about complex numbers, and in particular, complex conjugates. So if you write a complex number as z equals x plus yi, so real part and imaginary part, then the complex conjugate is defined as z bar, or z conjugate, equals x minus yi. So you just take the imaginary part and you take the negative of it. Then if you take z times z bar, or z times conjugate of z, then you get x plus yi times x minus yi, and this becomes x squared plus y squared. Because all the cross terms here cancel out, and the plus yi times the minus yi actually gives you plus y squared, because I squared is -1. And this is just the Pythagorean theorem. So in a complex number, the real part and the imaginary part form a kind of 90-degree angle to each other. So x squared plus y squared is just the absolute value of z squared. And therefore, we can write it s like this. So the absolute value of z squared, remember, is just equal to z times z bar. So therefore, the absolute value of s squared, which is inside this integral, is equal to s times s bar. So this sum. So now I'm just writing, I'm sorry about that sound, but now I'm just writing the sum times the sum with a complex conjugate. And most of the terms in the sum are just real numbers. The only part that's imaginary is, possibly imaginary, is this part. And I'm going to say that because of the way complex exponentials work, n to the power of sigma plus it, well, the complex conjugate of that is just n to the sigma minus it. But I'm just writing this second sum as a different variable, different dummy variable, just to communicate we're doing 2 different sums here. And then in this step, to multiply these out, we need to kind of consider this. So let me draw like a table perhaps. So 1, 2, 3, so forth. And then 1, 2, 3. And then this is the n's, and this is the m's. And we're just going to multiply all the terms together. Sorry, this is not a very good table here, but to multiply all these terms, so we have t terms times t terms, I'm going to have t squared total terms in this grid. And the first part of this thing is the diagonal terms. So when n and m are the same, we have these diagonal parts of the product. And if we just take this product and set n and m equal to the same, then the numerator is going to be d sub k of n times d sub k of n, so that's d sub k squared of n. And then the denominator becomes n to the sigma plus it times n to the sigma minus it. And the two sigmas add together to get 2 sigma. And then the it and the minus it add together to 0, so there's no t here. Okay, and then for the off-diagonal entries, maybe this is a better color. For all of the other entries in this grid, I'm going to write it like this, where the d sub k of n times d sub k of m is just up here, and then the sigmas are here. And the it here is due to the result that if you write n as equal to e to the log of n, then n to the it power is e to the it log n. And similarly, this is m to the minus it log m, or e to the minus it log m. And if you kind of add those exponents together, then you get like log of m minus n, but log of m minus log of n. But log of m minus log of n is equal to log of m over n. So that's how we're getting this. Okay, and then now remember, we don't care about the absolute value of s squared in itself. We care about the integral from 0 to t of the absolute value of s squared dt. So therefore, we can integrate this thing from 0 to t, so both of these terms. And then remember, the first term here does not have any little t's in it at all. So when you integrate from 0 to big T, d little t, then this is just a constant, so you just add a t to the end of here. And then this term actually does have a t. So most of this giant thing is a constant, so it stays the same. And then you just have to consider this integral. This is kind of a relatively easy thing to integrate. This is an exponential, and since you evaluate from 0 to t, you have this t term and then this 0 term. So e to the 0 is 1, so you get this 1 here. Okay, and then processing this a bit more. So we're going to process both this term and the second term, but we're going to do this first one first. This is the sum where n is less than or equal to t. And what we're actually going to do is we're going to write this as an infinite sum. So let's skip forward just a little bit. So remember, the sum from n equals 1 to infinity is equal to the sum from n equals 1 to t, and then the sum from t plus 1 to infinity. And that's going to be this term. And in a big O, you don't really care if the thing is positive or negative, right? So minus big O is the same as plus big O. So you can write that the sum, the first terms, 1 to t, is the same as the infinite sum plus O of the remainder sum from t plus 1 to infinity. And that's what we're doing up here. We're evaluating the sum where n starts at t plus 1. Okay, and then this thing is equal to big O of, again, using the integral test here. And you integrate this, and then you combine the exponents together, and you get this term. Okay, and then now we're going to process. Sorry, I'm going kind of fast here because there's a lot to go through. Then now we're going to process this term, which is quite hard. So up here, we're once again using the fact that, remember, d sub k of n is equal to n to the, as O of n to the epsilon for any epsilon. So I'm going to write this d sub k of m times d sub k of n as mn to the epsilon power inside the big O. And then here I'm using the fact that if you look at this term kind of carefully, then this thing is just bounded because a real number to an imaginary power, purely imaginary power, is just a number in the unit circle, which has a modulus of 1. So if something has an absolute value of 1 and then you minus 1, then that thing has the most absolute value of 2. Although in the big O, we don't really care about the constant, but I'm just writing 2 to make it clear how we got from this step to this number. And then finally, you can get rid of the I, and then I can say that take the absolute value of this log down here, So that's how we get from to this step. And then to get to the next step, notice I've taken, instead of saying m and n are not equal, I'm saying m is greater than n. And this is because, remember, in that product, you can think of, I took everything as a product here, so I multiply all of the diagonal terms, and then I have all these other terms that I'm multiplying out. And I'm saying that the sum over all of these diagonal terms is just 2 times the sum over one of the triangles. So I can just take the top triangle and then double that. So that's what I'm doing here. And then if I double it, I get a 4, but once again, I don't really care about the constant inside of big O, so this 4 becomes a 1, and then this epsilon and sigma become epsilon minus sigma, and that's how you get this term. And then we're going to continue this on the next page. So this is the same thing as before. And we're going to split out this sum into 2. So we're going to set m equals n plus r. And I'm going to note that 1 over log of m over n is bounded when m is greater than 2n. So for the part where so I'm going to split this up into a sum where m is greater than 2n and m is less than or equal to 2n. So the greater than 2n is first, and the less than or equal to 2n is second. And for the part where m is greater than 2n, I've kind of removed this log on the denominator because this thing is bounded. Remember, m inside a big O, so I don't care about a constant. And then to get to the next step, so hopefully that part makes sense. To get to the next step, I'm kind of reassuming that instead of taking all the terms where m is greater than 2n, I'm taking all the terms, even including the parts where m is less than or equal to 2n again in the sum. And that's just because in a big O, like, we don't care if we kind of increase the number by a little bit. So I can always try to make things larger, and then this thing is still a big O of the larger thing. So if I kind of reintroduce all the terms back and then split out this sum into a double sum, I can say the sum from m less than or equal to t, and then the sum of n less than m. And then I split out the m to the epsilon minus sigma and the n to the epsilon minus sigma. And then if you look at each individual of these sums, this thing is just O of 1. So I can remove that thing entirely. And this is because you can just pick an epsilon small enough to counteract the fixed delta or fixed sigma, such that epsilon minus sigma is less than -1. And if that's true, then this thing is just a kind of finite number, O of 1. And in fact, you can even if this were an infinite sum, it would still converge. But if it's a finite sum, it's certainly bounded. And that's kind of because the infinite sum converges. So this thing is O of 1, and this thing is also O of 1, so that becomes O of 1. So this whole left sum becomes O of 1. And then when we look at the right sum, so remember this is where m is less than or equal to 2n, so we can write m equals n plus r. And this log of m over n, so remember if m is equal to n plus r, then it's n plus r over n, which is the same thing as 1 plus r over n, because remember n over n is equal to this 1. And because I'm also saying that m is less than or equal to 2n, then I can write m as just something at most 2n. So this numerator is at most 2n times n to the epsilon minus sigma. So that's just O of n to the 2 epsilon minus 2 sigma. Okay, and then if you write the log as a Taylor series, then the principal term, or not, maybe the principal term isn't the right word, but the biggest term of that is going to be the r over n. The Taylor series of log of 1 plus r over n. And then you have something divided by r over n, so the denominator is still going to remain r, and I can move this n to the numerator, so multiply by n in the numerator. So that's why this thing becomes n to the 1 plus this exponent here, and then divided by r. And then finally, we're going to evaluate this double sum. So this double sum, the sum where r is between 1 and n of 1 over r, you can use the integral test again. So the integral of 1 over x is just log of x. So this r thing just becomes log of n. And then finally, you get this thing. But again, if we pick the epsilon such that epsilon minus sigma is less than -1, then that means 1 plus 2 sigma minus 2, or 1 plus 2 epsilon minus 2 sigma is also less than -1. So therefore, this power is still less than -1, and multiplying by log of n doesn't help at all because it doesn't do anything to this because log is smaller than any power of n. So therefore, this thing is also just bounded because even if this were an infinite sum, it would converge. So taking a finite thing will still be bounded. So therefore, this thing is also O of 1. And therefore, O of 1 plus O of 1 is just O of 1. Okay, and then now we can kind of put everything together for this s squared term. So the integral from 0 to t of the absolute value of s squared dt is equal to, remember, this is the original thing we got. And then we processed this term into these two things. And then above, we just processed this into O of 1. And these are, we've done in the last 2 pages. Okay, and then now we're actually ready to put everything together. So remember, sorry about that. Note that the Cauchy-Schwarz term, remember that 2u there, in the Cauchy-Schwarz term, that u squared is less than or equal to this integral times this integral, and we already know the 2 growth rates for s and r, where s, we just got from above here, is really just O of t. And in particular, the reason is that I can actually kind of cross this thing out. So remember, if 1 plus 2 epsilon minus 2 sigma is less than negative 1, then 2 plus 2 epsilon minus 2 sigma is less than, is less than 0, because I just added 1 to this thing. So this term is smaller than O of 1. So since we already wrote an O of 1 here, I can just cross this out. So this whole term s squared, this integral of s squared, is a constant times t plus O of 1. And therefore, this whole thing is just O of t. So I can say this s term is O of t times whatever the r term is. Remember, the r term we said before is O of t to the 3 minus 2 sigma plus 2 epsilon. And therefore, I get t to the 4 minus 2 sigma plus 2 epsilon. And therefore, u, being the square root of u squared, is just going to be O of t to the 2 minus sigma plus epsilon. Okay, and now I'm ready to combine everything together. So this is the original integral we were trying to evaluate, and we're almost done. So what we did is we evaluated the s by itself. Remember, the s term is this, which we got from the last page. Or this s integral is this term plus the O of 1. And then the r term we did first. That was maybe a couple of slides ago at this point, but if you remember that, it was just a relatively easy case. That's O of t to the 2 minus sigma plus 2 epsilon. And then what we just did is we figured out the u term is like this thing that we just got the square root of this. So it's O of t to the 2 minus sigma plus epsilon. And because epsilon is less than 2 epsilon, we can just absorb this big O into this term. And then moreover, because epsilon is kind of just a number we picked, whatever epsilon we originally picked, we can just pick epsilon divided by 2. So just divide whatever you pick by 2, and therefore this will become like this big O here. And therefore we've proved the theorem. For a fixed sigma greater than 1 and a fixed positive integer k, then this thing is equal to this. And then I'm not really going to explain this part too much because we don't really care about this 2k thing much. We really only care about the k equals 1 case, but I kind of wanted to prove it with the 2k part in case you care about the more general result. But what I really care about is the kind of integral with zeta squared, and I don't really care about zeta to the 4th or 6th power yet, at least not for today's episode. So the corollary is if we set k equals 1 and fix a sigma greater than 1, then you take limit as t goes to infinity of 1 over t of this thing, and you get zeta of 2 sigma. And remember, that's because if you set k equals 1, then this whole numerator is just 1. And this sum is just zeta of 2 sigma, and then these two other terms go to 0 if you divide by t and take t to infinity. Okay, cool. So this is nice. But now I'm going to make a much stronger claim. And I'm going to claim that for a fixed sigma, where sigma is now allowed to go below 1, so this is when sigma is greater than 1, but when sigma is between 1/2 and 1, then this kind of looks like this. Let me actually use a different color. So notice this looks exactly the same as before, and I'm going to claim that this is actually exactly the same as before, even though you might notice, if you look carefully, you might notice that this 0 became a 1. But I'm also going to claim that this doesn't really matter, and these are really still saying the same thing. And the reason you can ignore this thing is if you change the 0 to a 1 or any like finite number, like a fixed number, then the integral from 0 to 1 of this thing is just a bounded number. So when you take the limit of this 1 over t times this thing as t goes to infinity, then 1 over t times a finite number goes to 0. So therefore, it doesn't really matter for this integral if you start at 0 or 1 or any, like, even like 5 billion or something. You'll still be zeta of 2 sigma. So I'm claiming that these two things are saying exactly the same thing. And we're going to kind of prove this claim now. And I will note that in the previous proof of Theorem 1, I think I was trying to be kind of more careful than usual. But in the next proof, since I've claimed we've already kind of gone through most of the proof, I'm going to be a little bit less careful, just in the interest of time. So to prove this, actually, sorry, let me go back. So when sigma is now less than 1, that infinite series for zeta no longer converges. So I'm going to have to write a different thing for the zeta function. So remember, the zeta of s when sigma is greater than 1, we define it as, we didn't use these latter two terms, we just define it as the infinite sum of this thing. But what I'm saying right now is that if sigma is less than 1, then this infinite sum, if this were infinite, would not converge. So you actually have to write as a finite sum. So we're going to use this approximate functional equation that we already proved in episode 24. So it's a finite sum plus some error terms. And then notably, this sigma is allowed to be between a number that's just above 0 and 2. So therefore, we're allowed to go to the left of 1. And what I'm going to say is for a value of little t between 1/2 of big T and big T, and I'm going to set x equals t, then I'm going to say that zeta of sigma plus it is equal to this finite sum plus some O term, and I'm going to call that once again s plus r, and we're going to do all the same manipulation on the s plus r as before. And hopefully this part should be pretty trivial, how to get from this sum to this sum. Remember, we're just setting x equals t. And then probably this part looks very trivial as well. I'm literally replacing the x equals t. But you might be wondering, if you're kind of looking at this carefully, like what happened to this term? Like it seems like it just disappeared here, and I claim it also just became O of t to the minus sigma. And this is for a couple reasons. So one is, if you think about s minus 1, s minus 1, s is sigma plus it. The sigma and the 1 are kind of the real part of this, but it's kind of small, it's bounded. And the real part is that, or sorry, not the real part, but the big part of it is that this thing has a it on the denominator. And notably, little t is at least 1/2 of big T. So what I'm saying is that the denominator here is in some sense when t gets really, really large, when big T gets very large and little t gets large, then this denominator is roughly 1/2 big T. And the numerator, since we set x equals t, is t to the 1 minus s power. So the x to the 1 here kind of cancels out the t over 2 on the denominator. Remember, in the big O, we don't care about the coefficient in the front, the 1/2. So we just get a t to the 1 on the numerator and a t to the 1 on the denominator. So you can kind of cancel out this 1 here and the s term on the denominator. So then you're left with x to the minus s, and that's just minus sigma minus it. But again, in a big O, we don't care about the it part, so we just care about the sigma part. So this just becomes x to the minus sigma, and since x equals t, that's t to the minus sigma. Okay, so it's maybe a little bit confusing, but hopefully that sort of makes sense. So these two terms together give you O of t to the minus sigma. Okay, and then if you write this as s plus r, then we're once again going to do this kind of Cauchy-Schwarz inequality. We're going to start with the triangle inequality first. We're saying this integral is equal to the integral of s plus r squared. And notice that there's no 2k this time. We're just doing to the second power. And this, by triangle inequality, is less than this thing where you take the binomial expansion and multiply everything out. And once again, we're going to set this term equal to u, and then u squared is less than the product of these two terms by the Cauchy-Schwarz. Okay, and then now, as promised, I'm going to go a little bit quickly here and skip over some details. The easy cases are, so remember, we have to figure out the growth rate of this thing and the growth rate of this thing. The growth rate of this r term is relatively easy because we already said, this r is just O of t to the minus sigma, so this is pretty easy. hard case is S, and I'm going to, again, skip most of the steps here. I think even this has most of the skips stepped already because this is just exactly the same as before. We're kind of rewriting this finite sum as an infinite sum plus some big O term, and then we're evaluating this giant term over here. And then we're going to do the same thing where we split this sum into m greater than 2n and m less than or equal to 2n. Instead of getting O of 1 this time, we're going to get O of t to the 2 minus 2 sigma times log of t. And then if you kind of combine everything together, then this integral is less than this thing, and then this thing gives you, remember this thing got you 1/2 of zeta of 2 sigma times t with some error terms. Let's try to draw what's going on. So this s term became this, and then this term became this, and then this term became this. And then finally, I can kind of absorb this big O in here, and I think I can absorb this in here as well. So I just get this term in the end. And now, because this is the integral from t over 2 to t, I can actually just repeat this process, replacing the t with t over 2 and then t over 2 squared and so forth. Sorry about that. A finite number of times to get the result from 1 to t. So I don't need to go from 0 to t, I just need to go from 1 to t. So I only need to do this a finite number of times. And therefore, I will get the theorem for a fixed sigma, where sigma is between 1/2 and 1. Then this integral from 1 to t of this thing is equal to sigma zeta of 2 sigma times t, plus some big O term from here. And you might be wondering what happened here. So if you take 1/2 of zeta of 2 sigma times t, and then you replace t with t over 2, then you do the same thing. You get the integral from t over 4 to t over 2. That's going to give you another 1/4 of zeta of 2 sigma times t. So you get 3/4, but it doesn't seem to converge to zeta of 2 sigma. Like if it took an infinite of these sums, it would converge to zeta of 2 sigma, but if you only take a finite number of steps, how does that converge? Well, the thing here is, since I think it actually doesn't converge to this, but we are going to just take the limit here, because the remainder part can be thought of as a big O. So therefore, it's just some, like the difference between 1 times zeta of 2 sigma and let's say like 31 over 32 times zeta of 2 sigma is just a fraction, like just a non-number times zeta of 2 sigma. Therefore, it's a constant times t, and then that can just be absorbed into a big O term. And therefore, we have this corollary of, for a fixed sigma where 1/2 is less than sigma, which is less than 1, then the limit as t goes to infinity of 1 over t times the integral from 1 to t is, of this thing, is just zeta of 2 sigma. That's like this thing here. Because you're just dividing both of these by t, and then you are, like this thing, if you take 1 minus 2 sigma, now this exponent is negative, and this will go to 0. Okay, and then in the corollary from before, we had this thing was from corollary 1, and then this is the corollary 2. And then now I'm going to skip a little bit, so not going over the details, but we could go through the previous proof with sigma equals 1 to show that the mean value actually does approach zeta of 2 sigma. So I'm going to claim that when zeta is greater than 1, this limit is to zeta of 2 sigma. When it's between 1/2 and 1, it's also zeta of 2 sigma, and then when it's equal to 1, it's also zeta of 2 sigma. So therefore, we get corollary 3, which is for a fixed sigma where sigma is just greater than 1/2, then this thing is equal to zeta of 2 sigma. And then I'm going to note that this does not easily translate to sigma equals 1/2. So remember, I tried to look at this. What we're trying to do is we're trying to look at this endpoint, and I'm going to claim this is true for sigma equals 1. But if you try to this process for 1/2, then you get zeta of 2 sigma, which is zeta of 1, but that's a singularity, so it's kind of infinite. But nonetheless, you can actually still analyze what happens if sigma equals 1/2. So you just plug in 1/2 to the proof we did. And I'm going to claim that most of everything is still the same except for this step here when you're looking at the integral from t over 2 to t of the absolute value of s squared. Then you get this thing. And now instead of getting like O of 1 or O of some other thing, you get O of t log t. And I'm not going to go through all the steps just in the interest of time, but you can try to kind of follow through this if you want. And the rest of the proof is similar to before, and the R case is O of 1. And therefore, we're going to claim theorem 3, so the integral from 1 to t of zeta of 1/2 plus it squared dt is O of t log t. And I'm going to claim that this is in some sense the most interesting thing we proved so far, because remember, everything else we proved is still pretty interesting, but now we've actually proved something along the critical line. That's when zeta is equal to 1/2, or then sigma is equal to 1/2, and this is where all of the non-trivial zeros of the zeta function that have been found so far are on. So this is kind of the most important area or region of the zeta function to look at, that critical line, real part of s equals 1/2. And in fact, I'm going to claim that the growth rate is actually t log t. So remember, O is just a upper bound of the growth rate, but I'm going to claim without proving it for this episode, but maybe in a later episode we'll prove that the actual correct growth rate is t log t. And therefore, if you take this limit of t, as t goes to infinity of 1 over t times this, then you will get the limit of log of t. So remember, 1 over t times t log t is just log of t, and that is infinite. Okay, so then just to go over what we proved so far, for corollary 3 is kind of the next most interesting result here. For fixed sigma with sigma greater than 1/2, then this limit, this kind of mean value theorem, says that this limit is equal to zeta of 2 sigma. And that's kind of saying that if I took one of these vertical lines, although if sigma is exactly equal to 1, then there's a singularity here. So I have to start at some point above 0. So if you just take some fixed point above 0 and then start there and go up the line, then what we're saying is that the average value along this line is just zeta of 2 sigma wherever your sigma started. So if you took this green line, the average value of this line corresponds to this point, zeta of this point, and then the blue line corresponds to this point, and then the red line corresponds to this point. And again, every time I say average value of zeta, I mean this thing, the absolute value of zeta of sigma plus it, then squared dt. So it's not really the average value, it's the average value of zeta, absolute value of zeta squared. Okay, and then finally here is all the theorems we proved today, just in case you want to see them side by side. I'm not going to repeat them or anything, but that's it. Thanks for watching.